was nervous. I didn't want to pull the trigger on it because I had work to do.
Yeah, the moment you go and get it, the only reason I stopped was just 2 a.m.
Now we should be.
I knew there was a swimmers mechanic, I don't know how to get it, but on the keyboard, down the same way. The exact same way. There's some keys, but all the old keys were about the same.
I spec it.
Yeah. It's rewinding.
Okay, welcome back. Just fighting with the internet for a little bit, just my daily struggle. How did Wednesday go? Did you join live, watch afterwards? Is it on your to-do list of like, it exists, I'll get to it? What do we think? Join live? Okay. We got to meet my son. He joined the stream like for 30 seconds to say, I don't know, I forget what he wanted, like an apple or something. I'm like, dude, it's class time.
How old is he?
He's 7. Yeah. It went during COVID. They knew when my classes were, so they would run into the room and say like, we want something, like we want this. And I had gummy bears in my desk drawer, so I would like grab a bag of gummy bears and throw it out the door. So they would run to chase that, and then I could like finish the rest of the lecture, or at least pause or something. But yeah, it was a nice like throwback 4 years ago. Everyone's favorite time, watching everything through Zoom. So anything left over from like homework 0? Yeah.
So I did it a different route from what you did in the demonstration.
Okay. Sounds like instant fail.
It was a similar baby.
No, it's fine. There's more than one way to do like all these things. Okay. Are you saying like a different programming route, or like you open a different program?
It was the same graph, but they asked for like the v of t being greater than 0 and start for v of 0 at 3. So my graph starts out at 3 meters a second and then peters down to 0 with the sliding chair one. But yours was like a proper parabola. Is that okay, or should I?
Yeah, so there. So the main thing here that I'll pop open this guy. There we go. It's like when we have like a chair kind of sliding, and we know there's friction acting on it, we know there's normal force acting up, we know mg is acting down, so normal force is the weight of the chair, all that's equal. It's all like ma going forward, but when the chair comes to a stop, there is no more a, like, because we can't slide a chair and then expect friction to bring it back to us. So the main thing that's like kind of neat that you can do with Python that's a little harder to do like you can do it. Like you can solve for when is v equal to 0, so my function is this from time equals 0 through 3.178, like whatever that solution is, and then you have another function of like, and then it's equal to something else. But we're trying to get something where it stops and then it's either flat or it just stops. Like maybe we just say like that's it, when just cut it off right there. Those were the two kind of ways that I thought about it, but yeah. I mean, I guess you could like draw the parabola graph, right? And then just say like none of that, like manually say like nothing exists out here, this is all fake. It's just like a physicist's take on real friction. Cross it out. Does that help or no?
Yeah.
A little bit? Okay.
Mine was based on volume per distance, so the graph looked a little different. or not volume, velocity.
Velocity
So
versus distance?
I think it was over time, sorry.
Oh, okay.
As it continued, it would peter down to 0 because it started at 3 meters a second.
Yeah.
I just didn't know if that was the right way because I saw you made one that had 2 separate line graphs that overlap in one plot.
Like velocity time goes to 0?
Yeah.
Yeah. No, that one's really good. That's a great graph to put up because then you know like when does velocity cross 0. Main purpose here is like try out. So look at Python code, see if you can get, because there's examples of this. I went kind of from scratch, and it's like watching a cooking show of like, and now we need the emulsified eggs. Like, what are emulsified eggs? And you have to watch a different video to figure out what emulsified eggs are. And now you come back to the first video. So like everything was kind of pre-prepared because I've done it so many times and I've thought about it and I built the assignment. But yeah, a chance for you. And someone asked earlier this week of like, is it gonna get harder? Are we gonna have to do more and more? Are we gonna keep pushing our Python skills? Really, this is like harder than I'll normally ask you to do Python work. Like this is probably as hard as it gets. There might be weirder things where you come up with errors, but I'm not expecting you to like debug and get into the code. Like it's something, if it's not working, then you can ask a question. Like I'm not expecting you to become an expert in Python. You will anyway, but you're not being assessed based on that. It's just, this is just for fun. So let's just do cool things. Yeah, and especially this one, like, just for fun. And also get the hang of like, how do I open it? How do I print it into a PDF? How do I submit that PDF? Like all that process, all the extra stuff. Sound good? Other homework 0 quiz, and then there was so explanation videos are just for quizzes to answer lemon shark. So tart. So you don't need one of those videos like for every homework and project. Most of the homeworks and projects will work some in class together. I guess technically you could like watch everything online, and I'll never know if you were ever the author of that work, but we have ways, I guess. Yeah, I'll track your IP. Like, are you the real Mario at 163582? Not really. I'm not going to do that. It's too much work. You want me to check in or just forge ahead? Forge? Keep going? All right. I'll check in later, and you can always backtrack. Of like, I know I didn't say anything, but I don't know what Python is. Like, can you explain? Okay, then we're back to like homework 1. So we took a look at, I think, the first problem. Now I think we're on to the next problem. So I'll do same process that I did the first time, just as like a reminder. Where do you find this stuff? The reference material, video notes, there's always links to the UConn Library textbook. So now we're looking at chapter 1, 1.1. I'll scroll all the way down. All right. Now we're going to look at some vectors. we want to label RPO, RPQ, RQP on this little three-dimensional Cartesian coordinate system. There are two dots somewhere in space. What are these three vectors? Take a second, try to draw it out. What do you think this looks like? Yeah. Yeah.
Like P slash up.
Yeah.
P2 or P1.
All right, that's a great question. And it's a great way to start us off. All right, I know where O is, right? I know where P is. I know my vector is connecting the two, right? Is it going from O to P or P to O? What is P slash O?
2P from O.
2P from O. Does that sound right? Like that? What do we think? Does it look right? I mean, it's a vector, right? And it's 50-50. This is, at least for this notation, when you see like a PR, so R is saying like this is a vector, it's described, and generally R is position, like some kind of, what is the relative position of this thing? And the way I always read it is the position of P with respect to O. So, position of P with yeah, and that's what we're saying here, is that if it's a slash O, we're starting at origin going to P. Yeah. And for some reason, that Beer and Johnston, did you use that textbook for Applied Mechanics 1, like statics? Did you use that? Beer? Does that sound familiar?
Connecting.
Yeah, McGraw, Connect. Yep. It uses both. It drives me crazy because they use both definitions. People are like, "No, we've never seen this before." I'm like, "It's definitely in the Beer book." Like, and then I found it. I'm like, "Here it is." But then they're like, "Yeah, but look at chapter something else," and pull up a different chapter. And this vector, it's not the same notation. It is like OP. Have you seen that one? That's different. That's like usually like geometry is kind of uses this notation. Like if you're looking at geometric proofs, sometimes you write out where did you start, where did you go. But the slash is always with respect to. Long explanation, short answer. Start at O, go to P. Okay, two more vectors. Somehow, because we're asked to draw both, say which one
I do, and just here was it dies at 5, so it really held out for me. I was doing a quiz. I use the 5 seconds. Exactly. I can beat the game up and after struggle turn on it immediately die.
Which kind of difficult to apply these extensions. Or there's a line.
But like for vectors, I've never seen any.
Oh,
You're saying, how do I get to the coordinate and start?
So you can probably just. I know I should, I'm just gonna watch it. Okay, that's the honest. If you took it early weekend, you just. True, I'd be up all night.
All right, which one is this? Because I saw people draw like both arrows right on top of each other. This is position of, yep. Yeah, so it's P with respect to Q. If you started at Q, that's how you get to P. So P with respect to Q, like that. And then, like a vector is a vector, right? If I draw it right there, I could also say, will let me move it? Yeah, that's all right. I could take that same vector, draw it over here. A vector is only keeping track of direction and magnitude. So no matter where it is, it's still the same vector. And this is that opposite. Q with respect to P. We can also say like if we only drew one vector, you could say it's equal to the negative of the other vector, and then you only have two vectors drawn. However you're kind of thinking about it, keeping track of things. Easy so far, right? We got this. So now we'll go on to chapter 2. I'll just open up textbook. Chapter 2 is a lot longer than chapter 1, so there's like specific places where I think you should look at the readings. You don't have, if you want to read more, you're welcome to. If you just want to jump into problems or do it a different way, you can do it that way. I'm scrolling all the way down to 2.8. And I think it says the bar, right? Of the barbell, sorry. Of the barbell. So we're not drawing free body diagram of like muscles, or of, I'm calling him nickname muscles. We're drawing like what are the forces acting on the barbell, so the thing he's holding. What does that look like? And this question I like because there's always like a few different answers here. This one's 2.8. Was there a 2.6? I don't think so. Yeah, just 2.8. Yeah. All right, so barbell. What is the free body diagram of that barbell?
Curved force. Oh, curved force. Because if he's curling it from 90, yeah, all the way up, maybe he does full 90, or maybe he starts from dead bottom and curves up all the way.
Looking forward to the same.
That's true. It is an upward mold. Yeah. Is it kinetics? Yeah, that is. Just the force is not okay.
Okay, so you're thinking like the motion.
Gravity, which would be the weight, I think 135 pounds going down. And then there's the normal force. Well, not normal force, which is his him putting it upwards. Something. Yeah. Overthinking.
It is a normal force.
That's true, yeah.
Which is even because in this position,
That's true, because otherwise it would just drop.
he's probably providing
135, 75 pounds? No, 65. I don't know, like this is just keep curling 135. It's actually not so
So if you add
no, let's encompass the
what if he's like holding it still?
I'd still be the same. I'd assume that.
Yeah, but like
If it was standing still, then I think it would be still.
if your car is moving at constant velocity, right? The acceleration is 0, right? But if it crashes into a wall, that's a lot of force being so then, how would I would try to calculate steady velocity? How much force theoretically would it have if it's not accelerating? Because the acceleration is at 0, the mass is constant.
well, the acceleration comes from the acceleration stop.
Oh, you're right. It's the impulse. It's the impulse. Based on like the distance of time for it to crash. Yeah. This is so smart. So smart.
I'm reading this book.
Yeah, screen red is dude,
It's like, I don't know, yeah.
Probably the hate on it. Maybe he gets views from it. I guess like red policy is not that good. Well, it's because like even if you were right about this, I'm so against the majority. I was worried to believe you. You're like, yeah, but now it's a lot like the open space. Stare straight into it. I see people touch me. Not training on the best of just like right there.
So this is one.
Bicep pain is the worst possible pain to my sweat. I'll take leg pain over bicep pain. Pain all over is fine. I can't bend my arms, Chris.
You just go and lay in bed for like 3 days.
Yeah, stuff you should do about it. Like, you need to push, I literally can't extend it. Like, 160. I remember the first time I did this, and Justin was like, dude, I'm just gonna do something. He grabs my arm and he force straightens it. I punched him. What about the weight of the bar?
The weight of the bar. You want to add that one? It is. It's not. We'll call it WB. You could add it. You could like split it up half and half. Then I saw something like this. So this one. So the last one is kind of like a side view. That's why I was drawing like a circle like that. So what do we think? Is it okay to just draw this thing as like, take the whole bar, squish it into one single point, and say it has a weight and there's a force lifting it? It's okay?
Yeah.
Yeah. Why would we do that? Yeah. It's sorry? It's much simpler, right? Like this is a very simple problem. No matter what kind of next question you might have about it, it's pretty easy to answer. Like, how much weight is this person holding? It's like, well, the bar is 135 pounds, so he's holding 135 pounds. Like, you don't have to do any more vector addition. There's no, everything's all in one line. There's no sum of the moments. It's a nice, like, easy equation of like, if the bar is this much, you have to hold it. And all the other physics that might be involved, you're not worried about it. You're just trying to figure out, end of the day, how much weight is there. So then, is this middle one needlessly complicated? Are we just making our lives harder for no reason?
No, because if you do want to do those more complicated equations, you can
Okay.
use this to find the element.
Okay.
How the force is distributed.
Okay, so distributed force, like what are, I kind of drew it as if the hands are not equally spaced, and kind of on purpose, kind of also like happy accident. But if you grab the bar and one hand is 5 centimeters closer to the center than the other hand, there's two different forces on your hands because you're still trying to keep the weights parallel to the ground. So now you need to figure out, well, you don't need to. Your body kind of manually does it. But one arm is doing a different amount of work than the other arm because you're not holding this with proper technique. So that could be one way that we use same forces, but just kind of split them up and solve different kind of engineering problem. What about this last one? Now we're looking sideways. and we have like some kind of force, like our bicep is doing that force, and it's overcoming that weight. What's happening here? Is it missing anything? What do we think?
Captures the direction of the weight.
Captures direction, okay. Yep.
Yeah, but the bar's gonna be moving towards you.
But there's, yeah, so if we think about this as like F equals MA, my MA is now coming at me. Do you kind of see why that is? So what's missing here? How do we get MA to not come at me? It's got to be some. Sorry? Force opposite that one? Yeah. So we could just say like, and something. F opposite. There's just some kind of opposite force. What is that force? Where is it coming from? Yeah.
I mean, you're kind of just transferring your weight in the opposite direction to, counteract the weight coming towards you.
So your weight, so you think it's partly, so heavier people would have an easier time of keeping the weight away from this way? Like more mass means less work? What do we think that way? Maybe not? Okay. I like tossing out theories. Electromagnetic, I don't know, black hole theory. Where else could it come from? Yeah.
If you're holding the bar and your hands have a little friction.
Oh, you think friction to keep it from sliding?
Rolling towards you.
Okay, so maybe there's like friction, like the grip that you have. So the grip is there. Okay. Can your, so the way that you're kind of lifting this, if you think about it, like your forearm is kind of pushing against your body and moving up this way. Can your forearm change length? Hopefully not, yeah. On a good day at the gym, your forearm is the same length before and after. So there's a constraint force. We could call it like a reaction force, that your arm can't change length. So if you're moving something around the pivot arm, the pivot of your elbow, it can't get closer to your elbow without your arm changing length. So there's like, your bones are holding some of that weight as it moves around in that arc. And that when you're holding it directly down, there's like extension force. When you're holding it straight up, there's like some compression force. But it's easier to kind of hold something, like hold it flat like this rather than out at an angle. There's like less moment on your muscle because now your bones are doing all the actual lifting. They're just like holding a weight with a reaction force. Cool. Were there other approaches here? Did I miss anything? Because I only got like small cross section. Did you have other forces that you're like, you can't consider weightlifting without drag? Or we need a kinetic diagram, this thing's moving. Something like that. No issues? No issues from there. Is one of these more right than the other one? Like one should get more credit than the other free body diagrams? It's on no. For the exam. What is the exam? Yeah, what do you need on the exam?
Depends on the question.
It depends on the question, yep. This question said draw a free body diagram. So done, right? Yeah, we're done. So simpler is sometimes better, sometimes.
You gotta think like, is it fairies or is it not fairies?
I don't know.
All the loopholes.
All the loopholes?
Finding the loophole.
That sounds like elves. They sound like loophole.
Pixies?
Or pixies, yeah. Leprechauns. Some kind of gift of gab, right?
The Fae. The Fae.
The Fae?
Yeah, the Fae.
Oh, I don't know. Now I'm outside my element.
Isn't the Fae just like all inclusive?
Oh, that's racist.
All right, 2.9, we'll do some more, another free body diagram. This time, we're doing some luge. Not like, not a shot luge, like a sport luge. Why is it so small? Do you know what luge, the sport, is?
They rest on sled and they go down. No, it's.
Oh, yeah.
It's like
Yeah, it's not surf, so it's on ice.
Yeah, it's on ice. They rest on a board and they
Yep.
ride down like a paved out route down a mountain. It's
Yeah.
terrifying.
So they're doing like
Like a more dangerous
50 to
Yeah.
60 miles an hour down an icy
Oh.
chute.
First,
Yeah. So, well, head first is
one of them.
skull? No. Skeleton. Thank you. I'm like skulls? I'm like broken skulls, but skeleton. That's the one. Luge is feet first. And so you're on a sled with like metal rails going down an icy chute.
So instead of a
So here again, question is draw a free body diagram of the luge. And yeah, so all three of those were valid answers. And what we'll find for this one, there's multiple valid answers, and it depends on how you're using it. So let's lump the sled and the rider as like one thing. So everything's going well. They haven't like crashed and separated. So it's all one rigid body together. Or point mass, depending on how you're thinking about it.
So obviously force navigate this because it's on the slope, the force already increasing the duration of it. But since it's not strong enough to take it off the ground, gravity keeps it grounded, right? And then you've got the force of friction pushing against it. Is there? Is there? Okay.
Oh, forward, so that one's like down.
That comes from the wall.
They come from the component.
Relative to gravity. It does. I remember that physics equation where the guy goes down a icy hill with no friction. Then he hits a bunch of balls of friction in the back receding area. And I was like, is this three separate free body diagram equations? It's terrible. It wasn't that bad. It was three, like, it was frictionless, and then frictionless flat, and then frictionless. So basically just conservation. It was the free body diagram.
Yeah, I mean, overall, there's gotta be. Otherwise, if it was on the late or so there is some potential that you start like 30 or 40 meters up. There's an overall, yeah. Withdraw.
So I saw some different versions of this. Is this what? And then I'll show some other things that I saw some people kind of thinking about.
Okay, considering we have no other comparisons, yeah.
Listen to the person who actually eats different. It's the worst tasting of.
I just had some and just have teriyaki beef. I just had.
Okay, mushrooms are so objectively speaking, that isn't horrible. It's just subpar.
Was anyone thinking of this as like I didn't see any yet, but like we're looking at the person's like toes. Were you thinking about the curve, like coming around a curve? Was anyone thinking about it that way? So far it's all side views. Did anyone think of like a front view? What did that one look like? Yeah. Some.
This tastes like problems.
Tastes like cactus. How the fuck did they actually make a single solution? They cut it when they're baby, they call it baby muscles.
So like thinking about the front view as if the person's coming right at you. We still have gravity going straight down, right? And then normal force is still coming off the wall. Is there anything else here? Like acting kind of in this plane? Yeah. Friction drag, okay. Where's friction pointing? Into, right? Yeah. So something like some kind of X to say like into paper, force of friction, force of drag. Yeah. Is there friction going up the wall? Okay. From sliding back down, right? Is it friction that holds it up on the wall? Momentum? Is it momentum? Yeah.
I think it would be friction.
You think friction? Okay. So here's a question then. What is the force of friction? What's the coefficient of friction between metal and ice? Ballpark. Is it 0.5? 0.1? What's coefficient? What do you think? 0.1? 0.01, yeah. So it's somewhere around like 0.01 to like 0.001. So if you're designing a sled to go up on a wall and your hope is that metal on ice will hold it there, then you can have like an angle of about 0.0001, like less than a degree. So it can't be a big angle. It'll slide right back down. So there's something else there. Are we running out of time? Yeah, we're just about out of time. Was there? No. Oh, sorry. I saw a hand go up. So then we'll come back on. Yeah, it's Friday. We'll enjoy the weekend, recoup, and then Monday we'll come back and we'll wrap up here and then move on to next problem. Cool. Thanks.
No, they could. I think it's still going. All right, if they